all of you know here John, I think, John Smee. He has been with us, a friend of ours, a partner of ours for a long, long time, and thanks, John, for that. John will be discussing, what's going on not only with 5G but beyond, and into 6G. And so John, welcome. You are the senior VP. I don't want to go through everything, but very, very accomplished. And so we are really excited to hear your keynote. Thank you.
All right, well, thank you very much, Sujit, for that welcome. And it's really my pleasure to be addressing the CWC audience, and it's really so great to echo that point on having it in person. I think we're all, Zoom fatigue kicked in probably about 18 months ago, so it's really great to realize, like, hey, there's some advantages to doing things in person, and it's a little more informal and can be faster feedback and more interactive. So my pleasure, and I'll certainly do my best to keep exactly on time. And what's the end time for the talk? And I'll make sure to be within 10 seconds of the end time. Leave some good time for Misha.
You have 25 minutes.
25 minutes, perfect. Okay, so I think I'll be able to click through the next slide here. So when we look then at as Sujit said, we're in this kind of exciting era. It's 2022 now, right? So there's a lot of 5G in front of us, and at the same time, it's a great time to beginning 6G research. And it's something that's already been ongoing for several years now. Leading institutions like UCSD doing a lot of interesting longer-term academic research. And so looking at how do we put things together end to end. And I think even when I look at the CWC forum, one of the exciting things is this recognition that there's a lot of interesting challenges, whether it's RF, whether it's low power, whether it's network architecture, whether it's the role of cloud, or even different types of devices. And so this slide, what it kind of makes the point of really 5G networks are getting deployed globally at an accelerating pace. And so when we were having these original 2014, 2015 discussions, in here and in other places, there was that perspective of, hey, what are we going to do with 5G? When's it going to get deployed? And we've actually seen instead a huge industry pull to get those 5G deployments up and running, many, many different 5G devices. I'm holding here a device with 28 gigahertz, 5G sub-6, really impressive performance, goes to this end-to-end approach of the ecosystem. And so we're kind of highlighting on this slide that reality then of all of these different types of connections and different types of devices. And then kind of taking it to the next slide, it's also this perspective of transforming to industries. So even the next speaker, Misha, was speaking back in 2014 on things like industrial IoT and how do we do things like time-sensitive networking and back then the phraseology of a tactile internet at many universities globally as well. So what's kind of exciting about 5G is that digital transformation element. So when we look at value beyond a smartphone data subscription, there is a lot of innovation that's happening in digital transformation in general. So this quickly gets into business models, it gets into how the technology is deployed. It also gets into the value proposition. Are we making workers more productive? Are we improving factory uptime? Are we improving logistics in terms of delivering things? Are we improving medical outcomes? So all of those things also leverage significantly the role of communications. And this is not communications by a bunch of people plugging in Ethernet. So there's a broad recognition that these technologies are going wireless, these industries are going wireless, and that value is being created because of technologies like 5G, because of technologies like Wi-Fi evolving as well. So as we look then, this perspective of the connected intelligent edge. So connected in the sense it's wireless, intelligent in the sense that there's AI actually on the device. So obviously, yes, there's AI in a data center in the central cloud. At the same time, the emergence of edge cloud. So even Sujit's own research on the role of edge computing, on the role of edge caching, and looking at content delivery for multimedia, that's a huge important aspect in terms of some of these new use cases. So what is happening and where it's happening and why it's happening, those three questions are more intertwined in the 5G era than ever before. And so the kind of highlight here then is this perspective of not only the role of the RAN and the core network, but then also the role of these intelligence in the network, the intelligence in the devices. And we'll talk a little bit later in a few other slides on even how machine learning is making its way into 3GPP as an example, release 18 study item. Obviously a huge topic as well for 6G in terms of this beyond 5G forum. How do we better harness machine learning, data-driven design into that 6G era? So then kind of putting that time frame perspective concretely. So one thing that we can't always discuss is the role of the standards timeline. And we know commercialization follows standardization by about a year or two based on the particular technologies, deployments on the network, taping out new integrated circuits, new low power RF, end-to-end architectures. But what's important to understand is a lot of the 5G ideas were discussed in a Release 14 study item. So this goes back to pre-Release 15. Those initial 5G deployments were based on Release 15. And at the same time, we moved from Release 15 into 16 and 17. So broadly speaking, we can view the 3GPP releases, 15, 16, 17, as the first half of 5G standardization. They included technologies like moving to non-terrestrial networks in Release 17. It included technologies like V2X with part of Release 16, designing for industrial IoT in Release 16. So a lot of different technologies and expansion occurred during 15, 16, 17. And so right now, we would say we're at a point of inflection. We're making sure that the next 3 releases, the second half of 5G standardization, has huge steps in performance, capabilities, use cases, and having that all come together in a cohesive framework. So a large amount of industry and ecosystem work went into defining Release 18 itself. So I'll have a few slides to go through that because it's not a single release. It's really setting the stage for 5G Advanced. And 5G Advanced will span now the next 5 years. So we look at 2022 to 2027 ahead of, say, a 6G commercialization in 2030. So that's going to be also an important perspective that we're going to do our level best to take a lot of the technology vectors and bring them into 5G itself, and at the same time look at creative new ways of bringing them into 6G. So this is that kind of viewpoint of what did we need to balance when we were defining 5G Advanced. So one of the things we needed to balance was the role of, what are the immediate commercial needs? What are the long-term technology vectors? What do we need to do on the infrastructure side? What do we need to do on the device side? What do we do to make sure that we're balancing mobile broadband evolution and support for new verticals, new types of industries? So that was that broad viewpoint that was part of those initial 5G discussions, the famous 5G triangle of mobile broadband, massive IoT, critical communications. So that's continued as 5G's continued to expand into new applications and use cases. And so what's important is then the standardization content is done in a way that's matched to the economic needs and the technology advancements. So a lot of interesting industry deliberations went into defining what should be in that Release 18. So the reason we have this particular slide here is to give you that framework for the notion of the mobile broadband improvements into the actual system. So we have a joke at Qualcomm that, hey, MIMO never dies. And it's because there's always some improvement in antennas. It's because what we can do is changing all the time based on technology advancements. So even silicon advancement in baseband help us do better MIMO algorithms, and at the same time, lower power RF architectures, the role of massive MIMO in 5G itself in midband, or the role of millimeter wave 28 gigahertz type spectrum, 39 gigahertz type spectrum. So the importance then of deciding the role of downlink and uplink MIMO, things like mobility and coverage, there's still foundational improvements getting made in those technologies. At the same time, we're making sure to design 5G Advanced to better support things like augmented and virtual reality. I was just discussing with Misha from Ericsson this perspective of, hey, how do you optimize for 5G XR to make sure that value is being delivered into new applications and services? The other thing is non-terrestrial networks, designing connectivity between smartphones and satellites, or the role of different types of altitudes being part of that network architecture. So it's very interesting to understand that, yes, 5G is a big space, but it's being approached in a coherent framework across broadband evolution and support for new verticals. And kind of going through a couple of those examples. So this one is highlighting then the notion of 5G and AI, so artificial intelligence. So we obviously already have artificial intelligence, things like RAN intelligent controller, intelligence on the network side. The devices themselves have neural processors now, neural networks within the devices doing adaptive training and learning, and ability to apply those decisions more instantaneously. So it's important to understand the difference between long-term training and short-term inference when you're making a decision, and making sure you can do that stuff quickly. How are you doing channel estimation? How are you doing channel state feedback? As we had a lot of these discussions on things like channel estimation and MIMO and these gigabit per second data needs for 5G technologies, it was important to understand then the side link information, how much information was required defining the state of that channel so that we could do the beamforming, so that we could do the MIMO rank selection, so that we can meet those coverage targets. So that's another really important thing, that when we look at communication, it's not only about the data channel, It's also how we look at the control channels. How do we look at the access procedures? How do we look at the framework of what we call channel state information or side information for communication? Because as we're communicating over wider bandwidths with more antennas in different frequency bands, we also have to make sure we're designing for efficient spectral reuse in terms of all of these different types of technologies. So this is an example then of what's in scope for the Release 18 study item. And the fact that it's a study item is important because what it means is then it's a multi-year, probably 18 months to 2-year effort where there's not going to be a normative spec. There's not going to be a work item in Release 18. So it actually is going to be a cohesive effort to define what can we do, how should we do it, but it's not going to finalize the actual solutions until Release 19 and 20. So this is a great example of 5G advancing. Hey, let's make sure we take a big step in machine learning in 5G Advanced. So let's get it right in the Release 18 study item. Let's deliver that through Releases 19 and 20. And at the same time, looking more longer term at machine learning into the 6G era. Another topic then is IoT. So going back to that triangle and consumer IoT and massive IoT and industrial IoT. So Release 17 brought in RedCap, reduced capability, going to lower power, lower bandwidth, lower energy consumption, opening up new types of use cases for cellular connected IoT. And that is continuing even in Release 18 with what we call enhanced RedCap. And we call it NR Lite and NR Super Lite at Qualcomm. And it's this portion of bringing the technology complexity down, bringing the cost structure down, bringing the energy consumption down. So this is another example where 5G itself, to address a lot of these interesting IoT scenarios, is continuing to evolve. And then similarly, looking at things like augmented virtual reality, Release 18, the role of network coding, the role of interesting longer-term studies on QoS. So how do we make sure some of these future use cases, like outdoor augmented reality, where people are wearing glasses that look like the ones I'm wearing now for basically huge numbers of scenarios outdoor, not even like, indoor VR gaming in a living room. I'm talking widespread outdoor augmented reality. Those are examples where we really have to focus on capacity, coverage, latency, power consumption, distributed computing, what's on the devices, what's in the phone, what's at the edge of the network. So it opens up a lot of interesting challenges, and at the same time, it's a huge evolving market, both for consumer and for enterprise. So I know this slide is a bit of an eye chart, but it's trying to contextualize the amount of work in cellular that's gone in positioning and location technologies. So not only are we communicating in radar bands as part of the millimeter wave aspects, but we're also looking at, even across the different spectrum bands, how can the cellular technology do positioning and sensing? So the technology evolution in 3GPP on things like positioning are incredibly important because it opens up new business opportunities. If cellular networks are getting deployed, sure, it's about communications. At the same time, it's also about enabling precise positioning, whether it's for an indoor factory in a private network or whether it's for widespread outdoor logistics tracking. So a lot of interesting content has gone into defining that 5G evolution of positioning. And you'll also see integrated communications positioning sensing as a core 6G research track as we're looking even longer term at these technologies. So kind of pivoting now to what is beyond 5G itself. So if we look now targeting a 2030 era, what do we need to do to make sure we're looking broadly at the 6G use cases, the 6G technologies? We understand what's getting better in an evolutionary sense. We also understand the need for the industry to look at the revolutionary aspects, to combine those into the system. And so this is things where we talk of compute topology. And people would say, hey, is computing about cellular? Isn't that separate? Like you have computing and you have wireless and those are different? No, we would say they're much more intertwined now. So where computing is occurring, how it's occurring, when is it distributed, how do you do the distribution? What is defining that end-to-end performance to meet those latency targets, the power consumption targets, the KPIs? So things like computing topology, even the role of disaggregation in network architecture. As we know from 4G to 5G and 5G to 6G, an incredibly important part will be cost-effective upgrades. No one's going to rip out 5G and just depreciate all that deployment, say, hey, now let's start again fresh with a brand new 6G CapEx that has no reuse of all of that 5G deployment. So we have, as you said, 5 more years of 5G standardization. At the same time, we're already looking into how do we make sure the evolution from 5G to 6G, the additive network side, is done cost effectively. And so then when we look at the use cases, it's really important to understand it's only 2022 now, and we're talking 2030 to 2040 for 6G technology. And so it's not about perfectly predicting exactly what use case is going to materialize in 2031 versus 2035. It's really about understanding what do we need to be improving to deliver on some of this long-term vision. If we look at the medical opportunity, smart connected hospitals, or we look at a factory of the future, we can talk of a factory in the next 5 years. We can also talk of where do we need technology to be in terms of productivity, in terms of logistics and optimization in a 2030 to 2040 era of digital twins. So it's important to take then this long-term view of where are these different technologies going and how do we design a system that can intersect as many of these as possible. And it's not about doing it all in that first release of, release 20, release 21, 6G work item in release 21. It's really about making sure that we're taking a long-term perspective, recognizing that this broad portfolio of 5G technologies plus increasing 6G technologies can address more of these scenarios. And so this is kind of our visualization, if you will, going from the triangle to the hexagon as we look at this perspective of the mission-critical massive IoT mobile broadband in the 5G era and looking at what are some of the new dimensions we want to bring in. Things like real-time control, spatial perception, even looking at some of the social sustainability aspects. So when we're taking that broader view of 5G into 6G, it's about understanding what do we need to make better? What are the KPIs we need to focus on? And what's interesting, as engineers, we always understand it's not about an unconstrained optimization where you're increasing performance, increasing power, increasing bandwidth. Okay, so that's not super exciting because you can just keep adding carriers and increasing your bandwidth and increasing your power consumption. What's more challenging is to have the constrained multi-dimensional optimization. That's where things get interesting. That's where you intersect the business opportunity with pragmatic deployment, with the physical constraints, size, weight, power, bringing in the cost on the device side, the network side. And then also as we pivot into a more services-oriented architecture, how do we cost-effectively deliver new services? What is quality of service? What is quality of experience? What are the sort of guarantees that can be offered to enable a new service? So this broad viewpoint then of a more immersive platform heading into that 2030 era. That's really important for us to keep track of. And then similarly, as we move to the next slide, we view that this perspective of all of these connected devices. So what we do know to be true is the number of connected devices is going to increase. The amount of machine learning and data generated by those devices is going to increase. And then also the physical form factor of the human interaction with devices is going to evolve. So this is the merging physical, digital, virtual world. There's going to be more physical devices. There's going to be more virtualization of the user interface. And there's going to be this increased focus on data, on sharing data, on creating data. So what data is generated at the edge of the network? When is it processed locally? When is it shared with the RAN or the edge network processing? So a huge perspective of this merging of these physical, digital, virtual worlds also creates this value going back to some of those 6G vision use cases, this more immersive digital physical experience. And so when we bring that back to the network architecture side of the cloud, of the edge cloud, of the device, the connected intelligent edge, we feel that we're on this journey where 4G did massive, mobile broadband and brought in massive MTC. And then we look at the 5G addition of different verticals, the ultra reliable low latency communication, the vehicle to V2X communication for vehicle to vehicle, side link communication, and a lot of the topology changes, integrated access and backhaul, smart repeaters. So a lot of interesting stuff occurred in this 5G era. And as I mentioned before, we still have another 5 to 7 years of 5G itself. So as we pivot longer term to combining 6G on top of that 5G era, it's about designing for this merging physical, digital, virtual world and always understanding the role of latency, the role of privacy, the role of edge, because that's what's going to define the future network architecture. So the wireless constraints themselves between the network and the devices and the network in itself and the devices in itself, that's going to be incredibly important, but it's always important to view that within the architecture of the cloud itself. And so when we look at some of those examples for Release 18, augmented virtual reality, right? So this is some of that examples of what's coming next in those proposals. And we can also look at what's even happening in the ecosystem today. So Qualcomm, as an example, has a huge product line focused on augmented virtual reality, taking the sort of technology that's in a smartphone and looking at what does it need to do to better serve virtual reality, to better serve augmented reality. A lot of different architectures and content and spatial processing and multimedia engineering gets combined with that wireless engineering, recognizing that these devices are going to be wireless, they're going to be, beginning to be tethered, and then they're going to move to be untethered. So a lot of interesting engineering challenges to make this a reality. We can also look at the evolution of automotive engineering and what's happening in that ecosystem, connecting vehicles. The role of wireless is incredibly important here. And because all of a sudden, the amount of data generated in the vehicle, data shared within the vehicle. So not only do we obviously have V2X as part of 5G itself and Release 16 and beyond, but also looking broadly at smart transportation and the evolving aspects of that intersection. So for us, this is a really important way to look at that evolving ecosystem, transportation intersecting with smart city, intersecting with communications. And so then when we look at this broader viewpoint of the path to 6G, it's about understanding we're moving a different number of technology vectors, and at the same time, we're trying to keep a pragmatic approach to what are the business drivers, what's actually going to get deployed. So the goal is not to create an academic spec that's not deployed. The goal is to then combine a rich amount of technology evolution with a pragmatic approach of what needs to happen when, so that it can actually get deployed. And so this is some of those 6G research vectors that we talk about to help provide that context. So some of these technologies are going to make their way into 5G advanced, and some of them are going to make their way into 6G itself more directly. But it's important to then be pushing these vectors, and some of them are going to be constrained optimization, some of them we're pushing at the exact same time, other ones we're driving hard in a certain direction. As an example, there's going to be some panel discussions on intelligent surfaces this afternoon. A lot of interesting focus on that particular technology, how can it change topology? So that's just one small example where there's a lot of different stuff happening at the same time, but we have to make sure we're focusing on fundamental improvements, new ways of evaluating technology. I think that's another framework that I'd like to offer is that as we're driving these improvements, it's also very important to be able to understand numerically what is the gain in different scenarios. So what are we measuring? What are we evaluating? What are we simulating? When are we getting real-world data? If we look at machine learning and AI, it's also about where the data is stored, where the data is processed, how the data is shared. So if we look then at a little more information on some of these research vectors, you can click on these YouTube videos and you'll see members of the Qualcomm team who are kind of discussing some of these particular technology tracks. So I encourage you after the fact to click on these if you're curious about them, and you'll probably see several of these engineers participating in CWC in the next couple days as well. But it's really this perspective on the air interface innovation combined with an expansion into vertical markets, and just making sure that we're combining technologies effectively. And so then kind of finalizing here in terms of the timeline, recognizing that we're just embarking now on the 5G advanced standardization, with 5G advanced commercialization coming later. And at the same time, the time for that critical 6G research discussions, even as Sujit was saying, the naming of this group is the Beyond 5G Towards 6G Forum, and that kind of broad viewpoint of when was it a 5G forum, when is it a 5G advanced, when is it a 6G? I think it's so important to have that dual perspective as Sujit described, because it is about this perspective that we're going to be working on both of these technologies. There's a lot of interaction. We're going to try to bring as much content into 5G advanced to leverage those deployments, leverage those different types of devices that are already deployed. At the same time, we want to make sure we harness the full power of the technology evolution and revolution that's happening in adjacent industries in wireless and RF and baseband and compute. And so it's a very exciting time to be in the industry and to be academic researchers in this area. There's a lot of problems to be solved, and we have to work together to solve them effectively. So that ends my talk, and thank you very much, and happy to have any questions.
Can you come to the microphone?
I can introduce the speaker, Dr. Gabriel Rubiz. This will be a friendly question, hopefully.
Obviously. And let's assume that no one knows you, so introduce yourself.
Okay. I think John introduced me. So, John, you who have seen everything since 20 years, how long does it take from 5G, from starting to talk about 5G advanced to having full deployment of 5G Advanced, from starting to talk about 6G to having full deployments of 6G. And maybe in your experience of 5G before, from starting to talk in the standards committee to, 2020. Is it 6 years, 8 years, 5 years, just to have an idea of the timescale?
Yeah, so that's a perfect question from Gabriel, because then the short answer is, I'd hate to say all of the above, but it is something where some of the stuff is more immediate, where we can talk about a technology and we know, hey, we can get that into the standard in the next release. We can deploy it 18 months later based on an aggressive chipset architecture tape out, schedule. But at the same time, when we look at longer term technologies, then they might take more than 10 years. And I think one other big point of the cellular industry is recognizing that different vertical markets move at substantially different speeds. So you don't want to deploy, if we look at a smartphone, you might get a smartphone every year, a brand new model with new features, new capabilities, when we know the automotive ecosystem's moving in 5 to 6 year cadence. If you're connecting your factory, you don't want to deploy something and then have to rip it out, 1 year later. So there's an aspect where different technologies are moving at different gearing and timeline mechanisms. And so the talking about 6G now, the reason it's important to talk early, when that is truly 10 years away, 8 years away, if we're looking at 2030 commercialization, we want to talk about it early because we also want to get that long-term technology biggest steps, whereas the stuff that's more pragmatic, we can do faster.
Brian Johnstecker, Power Rocks. Thanks, John. Yeah, I always enjoy the, these visionary things, and I get all excited. I see this as the, it's okay. This is the path forward, right? And then a part of me goes, oh, wait a minute. We got to actually find a way to execute it and make it happen, right? Make it a reality.
Yep.
So, and particularly with, I'm biased to be focused particularly in the area of energy efficiency and stuff. So when I see things like, there's a need for, or improvement, whether it's in the standard or just, something you're driving in semis for driving, whatever you say, lower power or something like that. A lot of the time it feels like when you look at the holistic kind of overall view, it seems like a lot of time you're kind of playing whack-a-mole, like maybe things get much more efficient and lower power, say, at the receive end, but what's left out is it comes at the cost of having to kick things up at the transmit side, right? So the question of, at the end of the day, does the overall footprint, however you look at it, energy efficiency, whatever, is that better? So that, I guess that's one of the concerns, that the challenges that's kind of easier said than done, and maybe to propose a, kind of a more concrete, well, not exactly necessarily example or metric, but I guess maybe I feel like a challenge comes in being able to marry. It seems like there's two different sides. There's a focus on, kind of energy efficiency consumption from a system perspective, and then of course there's the QoS, spectral efficiency side.
Yep.
Right. So maybe if you can even opine or comment on what we do to marry those two, right? To have something that looks at, energy utilization, whatever, gigabits per square kilometer per watt megahertz,
yeah, like
or
bits
whatever,
per second. No, that's a great question. And so it is something we look at those more complex KPI, the multidimensional bits per second per hertz per joule per dollar, right? So you bring in those additional constraints because when we do look at cellular and the fact that these devices are now multi-gigabit per second, so there's been huge improvements, and that's obviously still happening with the handheld form factor. These can be charged once a day. Pretty impressive amount of communications transfer normalized over, say, the day in the life of a phone. And so I would say that, to your question, we are absolutely looking at, there's the network side of implementation, there's a device side, and so the amount of work in green networks, even in the last 15 years and what comes next, that is putting together this more cohesive framework you're talking about, and it is exactly how we are looking at device side, network side, air interface side, and an implementation side. And so it's very important consideration, and it's absolutely how we're focused on it.
All right, well, look forward to hearing more. Thank you very much.
Thank you.
Wait. I have a request. It is very important to get the naming correct. LTE, long-term employment. 5G NR, no retirement. Okay? 6G, what are we going to call it?
Yes.
Yes.
6G,
till death do us part, or something like this?
6G, live forever. Yeah, that's a good one. Yeah.
12G, and I'll retire now.
That's right.
Okay.
Okay.
We have a couple of minutes. Any other questions?
Okay, I think we can probably hand off. Or you one more? Okay.
I can ask one more. I think
Okay,
it's
great.
a simple topic. I'm Peter Gamble from Global Foundries.
Yep.
Certainly in the early discussion around 6G and even the technologies that we were developing, a lot of the, at least airtime was spent on discussions of communications above 100 gigahertz. I think now a lot of times people are really talking about 7 to 15 or 7 to 24. Where's your crystal ball in terms of frequency, usage, and utilization for 5G Advanced and 6G?
Okay, perfect question. So one thing is that we do fully believe that we're also going to use the mixture of new frequencies and old frequencies as part of 5G, 6G. So one thing is dynamic spectrum sharing between 5G and 6G will be interesting because 5G is pretty flexible. The bands like 10 to 15 gigahertz you mentioned are going to be incredibly important for new 6G deployments. Bands above 100 gigahertz are also really important from a technology understanding, investigation, RF sensing, wireless front haul, wireless backhaul. It's not a wide area technology, it's a local point-to-point technology. So we are absolutely, above 100 gigahertz is important. It is an area of research and technology application. A lot of the interesting new wide area opportunities, we're doing our level best to say, hey, how can we make 10 to 15 gigahertz look like 6 to 3.5 gigahertz? So you're 4 times higher in frequency, 3.5 to 13. So that means you have 16 times more antennas. You get that antenna gain. You get that, we call it gigantic MIMO, giga MIMO. So from massive MIMO to giga MIMO to enable bands like 10 to 15 to be part of that 6G wide area. But very good question from Global Foundries. Yeah, thank you.
Just one more quick question. Thanks. Surbit Sinha, Qualcomm. John, I had a quick question. So what are the direct technologies when we talk about green technologies? So what can wireless focus on in terms of environmental and sustainability aspects? So other than power efficiency, energy efficiency, are there any direct technologies or use cases that wireless can focus on?
Yeah, I would say some of the direct examples, you can get into link efficiency. You know, you can look into the PA side, you know, pre-distortion, post-distortion, link optimization side. We also know that the green technology is also about how you use the network. When are things powering off? So as circuit designers and engineers, we always understand best way to save power is do something quickly and then turn off. Avoid the leakage scenario. So you're just turning on at appropriate times. So that makes it multidimensional in terms of per application, how much energy is consumed. How much power is a base station radiating at 3 in the morning versus 5 in the evening? And so those examples are built into the more complex network architecture, cross-layer optimization. But at the same time, you're leveraging those improvements in the hardcore technology itself, the RF, the baseband, the circuit design, the role of machine learning to have more predictive understanding of usage versus reactive and averaging understanding of usage.
Thank you very much.
Okay,
John.
thanks very much, Sujit. Great to see you.